So already I have told that I will try my best to make my presentation in very lucid way, such that you should all keep awake after lunch. So this is my topic, ultrasonic wave propagation, how ultrasonic wave can be used for the characterization of material. And I will not really into the ultrasonic machining or anything like this, but I will use ultrasonic wave to characterize material defect or cracks or any degradation prior to crack formation, how it can be used. A very simple way I'll tell you, not so much rigorously in it, but give you some flavor on it. So this is the outlines. Basically, ultrasonic technique is basically one of the non-destructive evaluation techniques for the structural integrity of components. Non-destructive evaluation means without material, you can evaluate the structural components. Then I will be going to basic of some ultrasonic ND. Then I will just talk a little bit on some advanced ultrasonic technique that has been going on nonlinear ultrasonic. And finally, I will give one example how ultrasonic we have used for the assessment of the fatigue damage in a material. So why structural integrity is so much of important? Because of the reliable performance of any components of structures in a plant. Because this is essential, because in-service inspection as well as assessing of any in-service degradation of a material is very, very important for the safe running of the plant. So to ensure pre-service quality, we need to check any pre-existing defects if those are there, which may affect the performance of the components. And also, once the component is in service, we always need to have some regularly detect or regularly assess the components to avoid any catastrophic damage and loss of the structural integrity of the components. That's why structural integrity is very much important. So finally, the non-destructive evaluation plays an important role for the reliable assessment of the components to achieve, this is very, very important, minimum defect component with maximum confidence and reliability. Here are some uses of the ND methods, what we can do using several ND methods, fraud detection and evaluation in a component, leak detection in a pressurized component, pressurized vessel, any dimensional measurements, measurement of crack within a material or any material, structural and microstructural characterization, how the internal characterization occurs in the microstructure, estimation of mechanical and physical properties, elastic modulus, stiffness, density, everything can be done using NDT methods. Residual stress assessment or dynamic response measurements from the material, that can also be done using several ND methods. Finally, material sorting and chemical composition in mineral or wood industries, that can also be done using things. So there are various NDT methods. Basically, first thing, whenever we go to the doctor, so what doctor does, finally, doctor initially he tells us to show my eyes or tongue. Using light, he wants to see if everything is okay or not. So that means he always uses visual inspection initially. So this is the primary criteria for any non-destructive evaluation technique for the evaluation of the components. First, you see the visually, what is there and if there is any problem or not. Then comes to some liquid penetration technique. We use some liquid and put it on the surface. So this is particularly used for the surface or subsurface cracks or defect detection in the material. So due to capillary action, that liquid penetrates into the defects. So we can assess that something is there, which we cannot see in naked eye. Then comes to some magnetic methods. It may be magnetic particle method or some other advanced magnetic methods, suppose magnetic Barkhausen technique or anything else. This is applicable to magnetic material only. Then comes to ultrasonic. This is one of the best NDT techniques and most versatile technique due to its volumetric inspection. Till now, whatever I have told, visual, liquid penetrant or magnetic, everything is basically sensitive to surface or subsurface detection. But ultrasonic is a volumetric inspection can be possible using ultrasonic technique. Then comes eddy current technique. That is one of the electromagnetic techniques, which is very, very sensitive to the surface or subsurface defects and very minute crack, which cannot be detected in other technique, but eddy current can give you signal if something is there. And then X-ray, using radiography or something technique. But the problem is that using X-ray or radiography, limitation of the depth of penetration, that depends on the material. But I will be talking on the ultrasonic NDT techniques mostly. I will talk some basic ultrasonic technique. Before that, the definition, this ultrasonic technique is basically an acoustic wave when this acoustic wave, we basically send acoustic wave within a material which we want to inspect. This is elastic waves. This is very, very important, this elastic waves, because if it's a plastic waves, then material will be plastically deformed, just like shock waves. So this is elastic waves. So particle movement will be there, and particle movement will be done elastically in solid, liquids, or gases, and which have a frequency above 20 kilohertz. If there is a frequency spectrum in which ultrasonic lies above 20 kilohertz. For our NDE techniques, we generally use 20 kilohertz to 2 gigahertz frequency range. There are lots of applications. I have already told non-destructive evaluation for the structural integrity. Medical diagnosis, whenever we go some doctors or any pathology, they give us some ultrasonic inspection, and we always see what is there inside our stomach or in our stomach. So some fetus movement or something like that we can see in the image. That always uses ultrasonic technique. And materials characterization, already I have told, the inside whatever is happening inside the material, that can be done, that can be assessed using ultrasonic. The thing is that when ultrasonic wave propagates through a material, that ultrasonic wave interacts with the material, and that after interaction in the receiving side, whenever we will be getting some ultrasonic wave, we post process it, and we do some analysis. From that we do some we infer some information about the materials. So this is can you see the animation? Hello.
Yes, sir, we can see that. We can see.
Animation can be seen, no?
We can see animations.
Yeah, this is the animation how wave propagates through a material. See, every particle vibrates in its own position, but no particles move from one position to another position. That is, acoustic energy basically transferred from one particle to another particle like this, and the acoustic waves are propagated through it. So within that mean position, the movement or vibration of that particle is in the elastic domain. That's why no plastic deformation occurs within the material. So there are mainly for the basic ultrasonic testing, 3 types of waves are there, what we use for the non-destructive testing or for the evaluation of the material. First thing is that longitudinal waves, in which particle movement within the material and the direction of the travel of the wave are parallel to each other. They travel in the same direction. This is the longitudinal waves, which the velocity of which is related to these equations, that elastic modulus, Poisson's ratio, and density. So it depends on the longitudinal elastic modulus, Young's modulus of the material. Next comes shear waves, in which particle motion and direction of travel always perpendicular to each other. So at it you can see from the image that the particle movement and direction of travel are perpendicular to each other. So there are definitely a shear stress acting on that. So that's why this wave velocity is dependent on the shear stress. This mu is the shear stress of, and the shear stress is related to the Young's modulus or E, like this. So the important thing is that this wave cannot travel through fluids, or that is liquid or gases. So that's why this can be traveled only in solid. And next come the surface wave or Rayleigh wave. Sir Lord Rayleigh basically invented these things, mathematician. That's why this wave is called also Rayleigh wave. The surface wave basically travels through the surface of the material. Whenever we send from one point, that wave will be propagating through the material through the surface, and the depth of penetration of that wave will be depending on the wavelength of the wave what we are sending. That is, if the wavelength is lambda, so depth of penetration will be approximately lambda by 4. And if you go inside the material, the effect of this Rayleigh wave will not be there. So this is mostly can be seen during earthquake on the surface of the earth. So based on these 3 waves, we use the non-destructive testing. I will tell you something about how ultrasonic inspection can be done. We need to create ultrasonic wave first. For creation of the ultrasonic wave, we need one piezoelectric crystal. The property of the piezoelectric crystal is that if you give some electrical pulse into the crystal, so it will vibrate, and vice versa also. If you give some mechanical stress to the piezoelectric crystal, it will give you some electrical signal that you can see as a signal on the oscilloscope. So that is the procedure for creation of the ultrasonic wave. One piezoelectric crystal is there that we put on the material. If there is no defect, wave will be transmitted through the material and reflected back to the black surface. So we will be getting some echo. But if there is a crack and wave is propagating through the material, and few of the energy will be reflected from the crack, so it will be initially crack echo, and again rest of the energy will be transmitted to the other surface and reflected back from the back wall, and we'll be getting other echoes also. From there, we can see if there is a crack inside the material or not. And this is more clearly you can understand. So if there is no crack, only back wall, back surface echo is there. If there is a crack in the picture, you can see if there is a crack. So before back surface, there will be one crack echo. So from that crack echo, we know the velocity of the ultrasonic wave for the particular material, and we know that horizontal x-axis is basically a time axis. So we can convert it into the depth at which the crack is there, as well as we can measure the dimension of the crack. So this is very sensitive to surface and subsurface discontinuities. So this is the depth. The important thing, the depth of penetration for flaw detection is very superior to other NDT methods. Single access, only single-sided access is enough for the evaluation of the material using this technique. So whenever, apart from the crack detection in the material, we need to have something before crack, what is happening in the material, if we can predict something. So that's why if we use this ultrasonic wave, there are basically two parameters: ultrasonic wave propagation velocity and attenuation coefficient. We know that ultrasonic wave propagation velocity is mostly constant for a particular material, but if there is some damage or some deformation occurring within the material, so its stiffness or elastic modulus will be changed in the material. So as a result of which the velocity will be changed, because earlier I showed that the velocity of the ultrasonic wave is dependent on the Young's modulus or elastic modulus of the material. So that's why ultrasonic velocity will be changed. Another thing is attenuation coefficient. When there will be wave propagating through the material from the black surface or cracked surface, it will be reflected back, and there will be multiple reflection from there, because the wave is go up and down like this. So in the left side, you can see how the peak is decreasing and the amplitude is decreasing, and this decreasing is basically exponentially decreased, and the constant of this decrease thing is attenuation coefficient. The attenuation coefficient is due to the fact that if this is the material, you can see in the right side that some grains are there within the material, or some precipitates are there, some voids are there, or something is there. When acoustic energy will be propagated through the material, there will be scattering from the grain boundary, as well as particle or inclusions or anything else. So what happens if it's scattered everywhere? So in the receiving side, I will be having very less acoustic energy. So that's why my receiving side energy will be decreased. So it is due to the attenuation, which is mainly due to absorption as well as scattering. Scattering, I have already told. Some few materials are there, high damping materials, in which absorptions are there. If we send some acoustic wave, it will be absorbed. So due to which also amplitude will also be decreased. So now the thing is that whatever I have told, this is the basic ultrasonic or conventional ultrasonic technique, in which we assume that material is isotropic, homogeneous, linear, time independent. But in reality, it is not there. Real materials are basically having very complex elastic properties. Most importantly, nonlinearity is there within the material. So how to counter that nonlinearity within material using ultrasonic wave? Using whatever I have told now, using ultrasonic wave, if I send the ultrasonic wave within a material, I send very low power. So it only interacts with some macroscopic level of the defect or macroscopic features in the material. But if some nonlinearities are there within the material, then that nonlinearities may appear in very microscopic level. So those microscopic level may not be detected using conventional ultrasonic technique. Then we can go to some higher advanced ultrasonic technique. Suppose in fatigue damage, before crack initiation, there are lots of microstructural features that have been changed. Suppose dislocation, creation of dislocations, annihilation, dislocations piling up, cell formation, everything. After then, crack formations occur. So those phenomena within the material before crack initiation, that can be detected using this advanced ultrasonic technique, which basically gives us nonlinearity within the material. This is nonlinear ultrasonic. I will tell you just very briefly. Suppose this green color is one bell is there, and I am giving some sound wave using 440 Hz and 8000 Hz using these two bells. So this is the input signal. So I am having some, after my FFT frequency spectrum, I can see only 440 and 8000 Hz. But in the output, whatever we can hear in our in our ear, so output also will be 440 and 8000, whatever we are sending, if the bell is perfectly okay. But if there is a damage in the bell, in the second picture, there is some crack, suppose, same two bells I am giving, two sounds, two speaker I am using, 440 and 8000 Hz. So in input frequency spectrum will give you only 440 and 8000, but whatever you are hearing there, you will not get 440 and 8000, but other frequencies also. Why it happens? Whenever you go to the market to purchase suppose some clay pot, clay mittika pot, so how do you check that clay pot? You take that clay pot and give some ting sound on the pot and try to listen the sound coming out from the pot. If the sound is perfectly okay, then your pot is, you assume that your pot is okay. But if pot is not okay, then your sound will not be perfectly cling. It will be dung, this type of things. So why this is happens? This happens because whatever frequency I am sending in the receiving, whatever we are listening, that frequencies are the harmonics that we are sending. If we send F frequency, we will be listening to F, 3F, 4F, 5F like this. Higher the damage within the material, higher will be the harmonics generation. So those generation of the harmonics are the signature of the damage within the material. And this ultrasonic is very, very sensitive, much before the crack initiation. So don't bother about the fully mathematics. I'll just give you a glimpse. The first equation is the basic Hooke's law, but I have expanded it in series expansion. Some beta is the higher order, means second up to second order. This second order elastic coefficient. I have just expanded in series expansion the Hooke's law. The second equation is the conventional wave equation. So if I put this sigma from the nonlinear Hooke's law into the wave equation, I will be having number 3 equations, that is nonlinear wave equation. So this right hand second term in the right hand side is the nonlinear part, which accounts for the nonlinearity within the material. So beta is basically the nonlinear parameter. In the conventional ultrasonic, we have seen that ultrasonic velocity and attenuations, these two are the main parameters for the detection or evaluation. But in this case, this beta is the nonlinear ultrasonic parameter. If we solve these equations, there is a trick, and finally we'll get this beta is this. In the fourth equation, you can see number 4. K is the wave vector constant depending on the frequency you are using. X is the propagation distance for a particular material. This is always constant. This A2 is the amplitude of the frequency 2F. Means whatever I am sending, if I am sending frequency F, the amplitude of that F is the A1, and whatever I am listening, if there is a damage, so 2F will be generated. The amplitude of the 2F is the A2. So this generation of this A2 is the signature of the damage within material, which basically accounted into the beta. So this beta basically we measure from the material using this nonlinear ultrasonic technique. So coming to the final one example for how fatigue damage assessment we can do. We have done some high cycle fatigue damage in a copper sample, very basic material. This is not so much structural but basic material. In room temperature, load ratio of R is equals to -1, flat dog bone specimen. You can see my cursor. This is the gauge portion. So in this gauge portion, we have marked 1, 2, 3, 4 like this. And at every positions during fatigue damage, we have measured the ultrasonic measurement, both conventional ultrasonic measurement as well as nonlinear ultrasonic measurement. So this you can see, this is the right side top is the copper sample. So we have marked various points on the sample, and at various positions, certain positions, we have measured the ultrasonic measurement. This is the conventional UT. Earlier I told. First plot is the variation of the velocity before loading. Blue color is the before loading, and red color is the after 80,000 of cycles. The velocity changed. And the attenuation coefficient, that also you can see before loading and after loading, attenuation coefficient also changed. So our main intention is to check the position where the crack can be formed earlier, much prior to the crack formation, if we could tell. But from these two plots, the velocity and attenuation coefficient plots, we cannot tell effectively from which position it is failed. But in the attenuation coefficient, more or less we can see there is an increase in the attenuation coefficient at position 9 or 10 like this, the red color. Next we have done on the nonlinear ultrasonic measurement, whatever I have told. This is the plot for the before loading the sample, that is in virgin state. How the y-axis is the nonlinear ultrasonic parameter, that beta, what I explained, how it is changing, more or less constant. This is after 80,000 cycles. Just like we did in our conventional ultrasonic measurement, here also after 80,000 cycles, we can see at position 9, there is a huge increase in the value of beta. So the thing is that beta predicts that failure may occur at the position 9 from this plot. Then sample was further loaded in the machine and fatigued till failure. The sample failed at 27 into 10 to the 4 cycles. And surprisingly, the sample was failed at position 9. You can see in the picture that in position 9 crack formed. So this is the position. So beta could predict the onset of failure much prior to its occurrence, because this 80,000 cycles is corresponding to the only 30% damage of the material with respect to the failure cycle. So we can see how nonlinear ultrasonic is so sensitive within the material. But why it increased so much? Because before crack initiation, there are lots of dislocation movements that occur within the material. Dislocation generation, dislocation density will be increased. When there will be increased in dislocation density, so if we know that dislocations means some defects within the material, if we send some acoustic energy or ultrasonic wave, due to this interaction between acoustic energy and dislocations, there will be vibration of the dislocations, and due to these vibrations, the acoustic energy will be distorted, and that's why harmonics generated. If there is crack, we send some ultrasonic wave. Suppose this is sinusoidal wave, there will be tensile phase and compressive phase in the sinusoidal wave. Due to tensile phase, the crack will try to open up, and due to compressive phase, the crack will try to close due to during interaction between wave and crack. So due to closing and opening and closing phenomenon of the crack, the ultrasonic energy, whatever I am sending, that will be distorted. And due to this distortion, ultrasonic wave will give us the harmonics that we cannot get from the conventional ultrasonic technique. That's why before crack generation, in that particular position, there are lots of things that happened, microstructural things that happened, and those things can easily be predicted using this nonlinear ultrasonic technique. So that's why this technique is very, very sensitive to microstructural degradation and deformation in the material. So finally, I can conclude that non-destructive testing and evaluation is very, very crucial for structural integrity of components. Among all ND techniques, ultrasonic is the most versatile technique for material evaluation. So wave propagation velocity and attenuation coefficient are the two major parameters for conventional ultrasonic ND. But for nonlinear ultrasonic, this technique is very, very sensitive to microstructural degradation much prior to its failure. And the signature of the harmonic generation is basically generation of higher order harmonics. So this is all from me. Thank you for your attention.
Thank you very much, sir. It was a very indeed eye-opening presentation.